Hello everyone, my name is Shingo Kitagawa from the University of Tokyo. Today's topic is Miniature Tangible Cube Concept and Design of Target Object-Oriented User Interface for Dual-Arm Telemanipulation. In this study, we propose to use a Target Object-Oriented User Interface for Dual-Arm Telemanipulation, and we implemented the user interface as a tangible device. Background of this research is telemanipulation. Telemanipulation is object manipulation in teleoperation, and previous works are focused on user interface, sensor feedback, and control system with time delay, and they are focused on end effectors of the robot. They are categorized as end-effector-oriented user interface. It means that the pilot commands the end effector's pose and force input via devices or force feedback system, and the robot manipulates a target object with only end effectors. In this research, we propose target object-oriented user interface for telemanipulation, which is focused on the target object itself. So, what is the Target Object-Oriented User Interface? The left figure is End-effector-oriented User Interface, EEOUI, and the right figure is the Target Object-Oriented User Interface, TOOUI. In EEOUI, a pilot represents physical and geometric constraints of robots and effectors. But in TOOUI, a pilot represents physical and geometric constraints of target objects directly. And TOOUI in dual-arm telemanipulation situation, TOOUI can represent physical and geometric constraints in these three situations. First one is target object and robot. So the TOOUI can represent pose, force, and contact between a target object and robot. But it also can represent the constraint between target object and other target object. So it means adjacent and overlapping contact between target objects. And it also can represent target object and environment. So adjacent and overlapping contact between target object and floor and wall. But what is the advantages and disadvantages of TOOUI? Let me talk about the advantages first. First advantage is that it can easily express object manipulation with multiple contacts. In the previous slide shows that it can express the three types of constraints. The constraints between target object and robot, target object and target object, and also target object and the environment. The second advantage is that it can solve the difference in body structure so that the robot can search for suitable robot motions that satisfy the constraints represented by the user interface. So it is good for dual manipulation or whole body manipulation. The third advantage is that it doesn't require the real-time sensor feedback. This is because TOOUI directly expresses physical constraints on the target object. So it is good for poor network connections and high network latency environment. These are disadvantages of TOOUI. First disadvantage is that it can only deal with assumed physical and geometric constraints. This is because TOOUI requires motion planning in order to satisfy physical and geometric constraints. So we need to design the assumed constraints and corresponding motions. The second disadvantage is that it is limited to the shape and rigidity of the target object. TOOUI is designed to mimic the target object shape, so that TOOUI cannot handle objects that are far from the shape or the rigidity of TOOUI. The third disadvantage is that it is less real-time control system. This is because TOOUI requires a robot to plan and execute motions. So, what is the suitable application of TOUI? In summary, there are 3 advantages and 3 disadvantages of TOUI. The advantages are easy to express object manipulation with multiple contacts, can solve the difference in body structure, and no necessity of real-time sensor feedback. And the disadvantages are it can only deal with the assumed physical and geometric constraints, and it is limited to the shape and rigidity of the target object, and less real-time control system. So, TOUI is suitable for manipulation tasks with multiple contacts and less real-time performance. So, TOUI is suitable for dexterous manipulation in outer space. But how can we implement the TOUI? In our study, we implement TOUI as a tangible device. In our study, we focused on orientation and contact representation, and we use proximity sensors on the surface to detect contact and IMU to measure the orientation. Let me summarize our study here. Our research goal is telemanipulation with multiple contacts like dual-arm telemanipulation, and our proposal is dual-arm telemanipulation system with TOUI, and our methods are tangible device as a TOUI implementation and motion planner for TOUI. In our study, we made miniature tangible cube in this figure, and we also make motion planner for the miniature tangible cube. This is our proposing dual-arm telemanipulation system. It has 2 parts, miniature tangible cube and motion planner for miniature tangible cube. The miniature tangible cube detects contact and orientation using proximity sensors and IMU and transmits sensor data. And motion planner receives the sensor data and select and execute proper motion. So, let me talk about the first part, miniature tangible cube. First, I will talk about sensors on miniature tangible cubes. There are 5 proximity sensors on each surface board, VCNL4040, so 30 proximity sensors total on each device, and these proximity sensors measure the strength of IR reflection on object, and each surface is molded by silicone rubber to protect the sensors and circuits. And there are also 4 full-color LED on each surface to represent the contact states to the users. Then, this is the inside of the miniature tangible cube. There are IMU, LiPo battery, and single-board computer in it. IMU measures the accelerometer, gyroscope, and the magnetometer. And the LiPo battery supplies all electricity for LED, proximity sensors, IMU, and the computer. And we use Raspberry Pi 0WH for the computer. And this is a data transmission network of the miniature tangible cube. All proximity sensors and IMU inside the device is connected to the Raspberry Pi 0 with I2C connection, and all the sensor data are transmitted to the robot through wireless connection in ROS network. Next, I will talk about motion planner for miniature tangible cube. For the motion planner, we use the state machine-based method. We design a state machine for miniature tangible cube based on its contact and orientation states. Each node represents its contact and orientation states of miniature tangible cube, and each edge represents robot motion. So robot recognizes node transition from sensor data of the device and executes the transition motion. For the evaluation, we did 3 experiments. The first experiment is contact and orientation recognition. We did experiments to recognize the contact and orientation of miniature tangible cube, and the device could properly detect contact and orientation changes, and the device could transmit the sensor data, and we could visualize the data on another computer. And this is the second experiment, box lifting and tilting by miniature tangible cube. We did dual arm box lifting and tilting with miniature tangible cube, and the robot could lift up the box in left video, and the robot could tilt the box in x-axis in right video. And for the final experiment, we did box rotating with reholding by miniature tangible cube. We did dual arm box rotating with reholding by miniature tangible cube, and the robot could rehold the box during the rotation, and the robot could rotate the box to 90 degrees in z-axis in total, and it took 109 seconds, which is faster than VR controller case 131 seconds. For the conclusion, we did 4 main things. In this study, we proposed to use TOOUI for their telemanipulation, and we developed the miniature tangible cube as a TOOUI implementation, and we developed the dual-arm telemanipulation system with the device, and we evaluated the system with PR2. For the future work, we want to extend our system to the whole body manipulation motions using search-based motion planner. We also want to change the miniature tangible cube shape by splitting the device into sensor units and external structures. Thank you for watching.